Okay, so today we're going to take a look at section 1.7. Section 1.7, unfortunately, is all applications. Now, I did email over the weekend 2 documents to you. One of them was on how to classify word problems. The other one was actually the examples that we're going to work through today. So let's go ahead and take a look at those examples. When I do word problems, I tend to go fairly slow. We're only going to do 6. That's it, because it takes a while to explain through them. So example 1, if you looked at your document, if not, go back and look at it. I'll read it. It says, Wendy is a loan officer at our bank and she's got $1 million to lend. She's required to obtain an average return of 18% per year. If she can lend at the rate of 19% or at the rate of 16%, how much can she lend at the 16% and still meet her requirements? So you look at that and say, I have no idea what's going on. The first thing to do is to classify it, because the things that are mentioned in the problem are money and percent rates of interest. I'm going to classify this as an interest problem. And if you look at the other document, that's what I call these. So I'm going to make a chart. And the chart that I'm going to use is going to have in it columns. So the first column is going to be investment 1. So I'll abbreviate investment number 1. We'll also have investment number 2. And those are going to be my rows in that first column. This is just to help me organize it. That is all it's for, is just to help me write my equation. So the first column is going to be the amount. The second column is going to be the interest rate. And then if you remember from your basic formula work, that over here, the actual amount of interest is simply the rate times the amount. So this is going to be the amount multiplied by the rate of interest. So we're just going to multiply the first 2 columns together to get to that last column. Okay, well, what do we know? We know that she's got $1 million to invest. That's going to be our total amount. So that's going to go down here. That's the million. We know that her 2 investment rates are, sorry, looking back at the work, 19% and 16%. So she's going to invest at 19% and then again at 16%, and those are percentages. But she's required to get an average of 18% on the total investment. Okay, so when you do these interest problems or percentage problems, what you're going to notice is that you're given basically 3 percentages. You'll always have 3 levels of them. You'll have a small one or a weak one. You'll have a really strong one, and what you're trying to get is the one that's in between. So I look at these as terms of mixing like Kool-Aid. You take water and you take this really pretty colored stuff, and when you mix them together, you end up with something that's between the 2. So I have something that is weak, a small interest rate, something that's really strong, and we need to end up with one that's between the 2. So the number that's numerically in the middle should always end up on your total row. Okay, that's the information that is given. We know we have $1 million total to invest. We know we can invest at 16% and 19%, and we need to end up with an 18% return altogether. That's all they gave me. That's it. But there's everything given. So what we're going to do is we're going to come in and let this first spot be just X. So X is the amount of money that we're investing at 19%. So X is how much at 19%. Okay, now we're going to come in, and I don't know how much we are investing at the second one. But if I've used X for the first one, then whatever remains from that million is going to get invested at the second one. So this is always going to be the total number, that's the million, minus X. So in other words, if I invest 200,000 here, $1 million minus the 200,000, oops, need one more zero, is going to give me how much here. If I invest 500,000 here, then $1 million minus the 500,000 is going to go here. So if you have a number in the total spot, then this guy's always going to be that total minus our X. And at that point, believe it or not, the hard work's already been done. We're now just going to multiply across to get that right column over there. So at this point, I'm going to make these into decimals. So 19% is 0.19. I'm going to multiply it by my investment, which was the amount of X. So I have 0.19X. In the next row, we're going to take that 16%, 0.16. We're going to multiply it by the million minus X. That's pretty soft. And then on the final row, we're going to take that 18% and we're going to multiply it by the million. And there it is. Woohoo! Okay, you're looking at that saying, well, that doesn't look like anything I can solve. Well, what we're always going to do when we make this kind of chart is we're going to let one of the columns work for us. And what we're going to do is we're going to pick up this last column and write our equation. So in other words, our first investment is the 0.19x. We're going to add to that the second investment, which is 0.16 times the 1 million minus x. And that's set that equal to the total investment, which is the 0.18 times the 1 million. And there's our equation. Okay, so I want to go through that again really quickly in terms of how we wrote it. So what we did first is we made up our chart and then we filled in the information from the chart. We were given the total amount of interest, or the total investment of $1 million and the 3 interest rates. So the middle interest rate in terms of numbers always goes on the bottom. Doesn't really matter where you put the other 2. I just put them in the order they were given in. Then I'm going to multiply it, Then we came in and let the investment number 1 be our x, our variable. So we know that the investment at the second interest rate is $1 million minus x. Then we multiplied it across, and then to write the equation, we take that final column and write it as the first investment plus the second investment equals the total investment. And at that point, we're down to the algebra. So now we're just going to solve this nice linear equation. It's linear because all the x's just have a power of 1. So what I'm going to do is go ahead and multiply. So we're going to distribute this 0.16 in. So we'll end up with 0.16 times $1 million is 160,000. 0.16 times that x gives me negative 0.16x. And on the other side, we'll distribute the 0.18 or multiply it by the million, and that's going to give me 180,000. Okay. So let's combine our x variables together. 0.19 minus 0.16 gives me 0.03x plus the 160,000 equals the 180,000. We'll move the 160,000 to the other side by subtracting. That's going to give me my 0.03x is equal to 20,000. Then we'll divide out that 0.03. And this one has a really goofy answer. So when I do that, you're going to get x equal to $666,666.67. So a really bizarre number. So it's all sixes, and I'm going to round it to, because it's money, to pennies on the end of that decimal. But we need to recognize what that is. So I go back to my chart to identify that, and that x was how much we invested at 19%. So that was at the 19%. If I reread my question's asking me how much they invested at 16%. Well, I need the other one. So in order to find the amount at 16%, the chart is telling me to take my million and subtract that number. So at 16%, we're going to take our million. I'm counting my zeros to myself. Minus the $666,666.67. And that's going to give us 333,333.33, and that's at the 16%. So to answer the question, we need to invest that amount of money at 16%, the rest of the money at 19% to end up with an average return of 18%. And that's the investment problems. For some of you, I think that these are the most challenging of the group that we will do today. Does anybody have any questions about how we approach that one? Again, first I classified it. I made my chart. Once I made my chart, I could then write my equation to solve it, and then make sure that I'm actually answering the equation or the question that they're asking us. So, okay, any comments about that one?
I'm okay on that one.
Okay. Yeah. Okay. We'll erase.
The chemistry ones have been the mixing of solutions are the one that always get me. These ones I can do okay, but.
Good. Well, and so the goofy thing you say about that is, believe it or not, I'm going to use the same exact chart for those chemistry ones with the mixture ones. The only thing that's going to change instead of an investment, an interest rate, is it's a percent solution. So we do have one of those as example 6. We'll work one of those. So, but it's the same chart. Okay, example 2. is a different type of mixture problem. It's mixing coffees. So example 2 says a coffee manufacturer wants to market a new blend of coffee that sells for $3.90 a pound by mixing coffees that are $2.75 and $5 per pound respectively. What amounts of each coffee should be blended to obtain the desired mixture if the manufacturer needs 100 pounds? So this is actually very, very similar to the one we just did. I'm going to use a very similar kind of chart. What I'm recognizing is that I'm mixing 2 things together to end up with a third one. So we're going to do the amount. So that would be in terms of pounds. So that would be the amount, and that's going to be in pounds, LB for pounds. The next, instead of having an interest rate, we actually have a dollar amount. So this is going to be the dollars per pound. That's the pricing. And over on this other end, we're going to take the amount and we're going to multiply it by the dollars per pound. Now, from a chemistry point of view, this should make a lot of sense because the pounds and the dollar per pounds are going to cancel out, leaving us with just dollars. Okay. So over on the side, we have whatever you want to call them. So mixture 1, so mix 1, mix 2, and the total. In other words, what we want to mix together. And I'm always going to start off by putting the middle column in because to me it just makes more sense to get those 3 numbers on the price per pound in correctly. So we know we've got 3 numbers. I'm going to erase these in a minute. So we've got one that's $3.90 a pound. We've got a $2.75 a pound. And we've got a $5 a pound. So just like we did before, we've got a small number, a large number, and one that's in the middle. So the one that goes in the middle is always going to be on the bottom because, again, you're taking something that's pricey and something cheap, mixing them together to sell for in between. The other 2 numbers don't matter where you put them, so I'm going to put the $2.75 in the front, and the 5 is the middle. So, okay. So again, the middle of those 3 numbers is always going to go on the bottom of those, the bottom row. And then what else do we know? Well, all we know is that we need 100 pounds of mixture, so that's the total mixture. We're going to put that in as 100. Okay, and we'll do the exact same thing we did last time. We don't know how much of mixture 1 we're going to do the cheap stuff, so we're going to put $1 there. I'm sorry, X there. And then because we know we need a total of 100, this is going to be 100 minus X. So again, it's always the total minus the X. That point we'll multiply across. So this will give me 2.75X. This will give me 5 times 100 minus X. And it's okay to drop the decimal if they've got zeros after the decimal because they're not going to impact anything. And then the final multiplication across is going to give us the 3.9 times 100. If you want, you can actually physically multiply that there. It's up to you. I tend to not do it until I write the equation. But now we can write our equation. We're going to do it the same way. We're going to take the first mixture plus the second mixture and set it equal to the total mixture. So our equation becomes 2.75x plus 5 times 100 minus x. And that's going to be equal to 3.9 times 100. Yay, and there's our equation. Okay, let's go solve that. So we're going to come in and distribute, get rid of all those parentheses. So we'll have 2.75x plus 50, that's 500, sorry. That's 5 times 100 minus the 5x equals 3.9 times 100 comes out to be 390. Let's go ahead and subtract our x's. So 2.75 minus 5 gives me a negative 2.25x, which you start to panic about, but don't worry, things work out. Plus the 500 equals the 390. We'll go ahead and move the 500 to the other side. That's going to give me, I know I'm a little low on the board, so I'm going to move over here. That's going to give me a negative 2.25x equals a negative 110. And then finally, we'll divide out the 2.25, the negative 2.25, and the negatives will divide out, so it's okay that you got a negative because it's going to divide out. And then I just need to take 110 and divide it by 2.25. And when you do that, you get 48.9. And that's in pounds. And that would be, and according to my chart, I go back, X is the 275. So you need 48.9 pounds of the 275 coffee. But they want to know how much we need to mix of each of them. So they're also asking me for this 100 minus X. So if I take 100 and subtract the 48.9, so 100 minus 48.9 is going to give me what, 51.1 pounds of the more expensive coffee. So in this case, you're almost splitting it, just about 50 pounds of each to mix that 390 coffee. So you're going to do one that has you mixing, I think it's nuts, and then another one that has you mixing teas, very similar in nature to this problem. So, but again, the same thing I did is I made my chart, I filled in my chart just to organize things, and then I used that last column to create the equation and then solve the equation. So that's a mixture problem. We'll do another one of these in example 6 that's got the percent solutions that Rich was talking about. Any problem with mixing the coffees together?
I'm okay.
Okay, that means I can erase then. Okay, example 3, we're going to switch gears totally. The first two I think were similar. Example 3 is a motorboat. I know how much you guys do not like these problems. A motorboat heads upstream on a river that has a current of 3 miles per hour. The trip upstream takes 5 hours. The return trip takes 2.5 hours. What's the speed of the motorboat? Assume that the boat maintains a constant speed relative to the water. Okay, so we have switched gears. We don't have money. We don't have coffees. We don't have dollars per pound. What we do have is speeds. So what we're going to use here is the formula that distance is equal to rate times time. So D for distance, R for rate, and T for time. The other thing that is important to recognize is that if you're going upstream, you're going to be going slower because you're fighting the current. If you're going downstream, the current is helping you and you'll be going faster. Okay, so what does that mean in terms of our problem? So what we're going to do is we're going to come in and let, and I'm fairly descriptive here, R be the speed of the boat. And that's what we're trying to find as our variable, is how fast that boat is going. Okay, so they do tell me that the speed of the stream is 3 miles an hour. So 3 is the speed of the current. Speed of the stream. So that means that if I'm going upstream, that the stream is slowing me down by 3 miles an hour. So that would be R minus 3. If I'm going downstream, then that's pushing me along by that 3 miles per hour. So that speed would be R plus 3. Okay, so you do the same thing if you're in an airplane and you're fighting a tailwind or a headwind. If you have a tailwind, it's speeding you up. If you have a headwind, it's slowing you down. What I'm going to do is the same kind of analysis. I'm going to use a chart just to organize my information. The chart's a little bit different in terms of the columns. So I have distance for D, I have R, and I'll have T. So notice that it looks just like the formula that distance is the rate times time. Okay, and I didn't quite leave myself enough room. So I'm going to call one of these upstream and the other one's going to be downstream. So we're going upstream and we're going downstream just to get some titles on what's going on. Okay, now we'll finally start putting the information in. In terms of going upstream, we just said that the rate to go upstream is R minus 3. So literally I'm going to plug R minus 3 in there. To go downstream, we know it's R plus 3. So it's speeding me up by that 3 miles an hour. They also give me the 2 times. It says the trip going upstream takes 5 hours. So that would be my time. The trip downstream takes 2.5 hours. Okay. So they don't mention anything in terms of distance, but let's think about this. So if this is the dock, so here's the dock, here's my boat, not a very good boat, but I'm going to go upstream and then I'm going to turn around and come right back downstream. Haven't I gone the same distance both directions? So if you leave from Pueblo and go someplace and then back up in Pueblo, you've gone the same distance both ways. So what it really means over here is this distance is going to be 5 times R minus 3. And I really didn't leave enough room. So that would be 5 times R minus 3. And the distance down here is going to be 2.5 times R plus 3. So 2.5 times R plus 3. And then we're going to set those two distances equal to each other. So again, what we're saying is the distance that you go up is going to be equal to the distance that you go down. So I'm going to take my 5 times my r minus 3 and set it equal to 2.5 times r plus 3. So it works out really nice. And there's our equation. Now, sometimes you will need a third row down here for a total distance, but not in this equation. We just tell the distances are the same. Okay, now we can go solve. So let's go ahead and distribute. So that'll give me 5r minus 15 equals 2.5r plus 7.5. Let's move all the r's to the left side. So that's going to give me 2.5r minus the 15 equals 7.5, and then we'll add the 15 across. So we'll get 2.5r is equal to 7.5 and 15 is 22.5. And then we'll divide. So r is whatever 22.5 divided by 2.5 is, and when I worked that out earlier, I got 9. So r is equal to 9. And that's the speed of the boat. So that's in miles per hour. And the only reason I know that's in miles per hour is because they told me the speed of the current was 3 miles an hour. So everything's measured in 9 miles per hour. So again, we established what the rates were. We knew the times because they gave us that. And we know that distance is rate times time. So we simply multiply these two quantities together. The key here is that you're going to set the distance upstream to the equal to the distance downstream. So then that gave us our equation, which we could solve to get our answer. And we've answered the question because they want to know what's the speed of the motorboat, and that's what we found as our answer over here. A lot of times with these, they'll ask things like how long did it take or what's the distance. We could figure out the distance. It'd be really easy. We could take the 9 minus 3, which is 6. 6 times 5 is 30. So you went 30 miles upstream and 30 miles downstream. So just depends on what you want to do with it and what they're asking. Any question with the distance, rate, and times? I would not put, and I did not put one of these on this week's quiz, and I won't put one of these on the exam because I know you guys do not enjoy these. I stuck with the mixture kinds of problems because I think they're easier for you guys. So, comments or questions?
Makes sense.
Okie dokie, then that means I can move on. That's all I need. I just need feedback to know if we're ready to erase and move on. Oh, we're halfway there. We only have 6 examples, so we're getting there. Okay, example 4 moves on to another type. Okay, example 4 says, Trent can deliver his newspaper in 30 minutes. It takes Martin 20 minutes to do the same route. How long would it take them to deliver the newspapers if they worked together? Okay, so this is what I call a work problem, because the only thing that is mentioned here is the amount of time. So you know how much time it takes for the first person, how much time it takes for the second person. You're trying to find the time together, or you could be given one of the other variables. What we're going to use is a really specific formula. So this is the one place where we'll use a formula. It's a little bit different than one that's in the actual textbook if you can find the ebook and are reading it, but it works really good for us. So we're going to use 1 over the first person's time. So however long it took the first person to do it, plus 1 over the second person's time. So however long it took the second person to do it. And that's going to give you, or equal to, 1 over the time working together. Time together. Okay, and that's it. So the reason it works is because what you're doing is figuring out what fraction of the whole that each person does in terms of 1 unit. And so it works really nice for us. So we know that it took Trent 30 minutes. So I'm simply going to do 1 over 30. That's Trent. It also took Martin 20 minutes to do the same thing. So that would be 1 over 20. And how long is it going to take them together? I have no idea. So we're going to do that 1 over a variable. I'm going to use t for time. And believe it or not, that's all there is to the equation. So 1 over how long it took Trent was first, sorry, plus 1 over Martin's time is equal to 1 over the time together. Okay, these are a little bit harder to solve because you have to deal with the fact that there's a fraction. So we're going to multiply everything by the common denominator. In this case, the common denominator is, well, 30 and 20 will both go into 60. And then because there's a t, I'm going to use t as part of that common denominator. So we're going to multiply every single fraction by 60t. We're going to multiply this guy by the 60t. I'm going to write it out in front. I'm going to multiply this guy by 60t. And we'll multiply this last fraction by 60t. Okay, let's do our reducing of our fractions. So 30 goes into 60 twice, but you still have the t. So once I've reduced that, I've got 2 times the t. From the next fraction, the 20 goes into the 63 times, so that'll give me a 3 times the t. And on the other side, what cancels in this case is the t, and we're left with the 60. So let me go through that again just to make sure everybody's got it. So 30 goes into 60 twice times the t, that gives me 2t. 20 goes into 63 times, so that'll give me 3 times the t. And on the right side, the t's are going to cancel, leaving me with the 60. Well, that's fairly easy to solve. We can add those together, get 5t equals 60. We'll divide out the 5, and we'll get t is equal to 12. And that's going to be in minutes, and I know it's in minutes because they gave me the other 2 times in minutes. So in other words, if it takes one person to deliver the newspapers 30 minutes, the other person took 20 minutes, if they work together, it's only going to take them 12 minutes. So I really like these. I think they're cool problems. As long as you remember the formula, they're the easiest ones we do. Okay, any comments or questions about those?
If you leave the variable, so let's say if you just take a least common denominator of 60, is it still solvable, or do you have to bring the t over to the left side?
Okay, so if we used just the 60, then what we would have would be 2 plus 3 equals 60 over t. So that would give me 5 equals 60 over t. And at that point, I'm going to do that cross multiplying. I'd get 5t equals 60. So you'll still get the same answer, but just don't drop the t on that right-hand side. So it still works.
Okay.
It's whether or not it's more steps or less steps for you. Okay, good question. Thanks for asking one. Anybody else? Okay. Moving on to example 5 then. So example 5, we're going to go on to geometry because we haven't done a geometry kind of problem. So it says a gardener has 46 feet of fencing. So 46 feet of fencing to enclose a rectangular garden that has a border 2 feet wide surrounding it. So a 2-foot border around our garden. If the length of the garden is to be twice the width, what will the dimensions of the garden be? So anytime you have a geometry kind of problem, rectangles, circles, anything like that, draw yourself a picture. So here's our garden. It's my rectangle. They do tell me that the length is twice the width. So if I let the width over here be w, then this is 2w. So they do tell me that information. It also tells me that I'm going to put a border around my garden, and maybe that's to walk around the garden. Maybe it's a rock path or a concrete path or whatever, I don't know. So we're going to put this border around the outside of the garden. So, and I know that that border is 2 feet wide. So the inside piece is the garden, the blue is the border around it. So here's our garden. Okay, well, what do we know? Well, because we want to put the border around the outside, they're telling me to use the idea of perimeter. And I know that because the fence goes around the outside. And the fence is going to be along this, it's on the blue. So the blue represents the fencing. So we need the perimeter for the rectangle. The perimeter of any rectangle is twice the length plus twice the width. Normally I would tell you to look in the front cover of the book, but you don't have the book. So you can go Google search if you don't know that formula. So the perimeter is twice the length plus twice the width. But we need the length of the fencing. Okay, so this is where it gets sneaky. we know that in the middle of this, there's 2W, but I know I've got 2 feet of border on this side and 2 feet of border on this side. So the entire distance across that's getting fenced is the width of the garden, I'm sorry, the length of the garden, plus the extra 2 feet on both sides, which gives me 4. So L in this case is 2W plus 4. I'm adding on 2 for the left side and 2 for the right side. Well, I can do the same thing for the width over here. I know if we have W in the middle, I have 2 on this side and 2 on this side. So if I add that all together, that's W plus 4. So the overall length that is getting fenced is 2W plus 4, and the overall width that is getting fenced in is W plus 4. Okay, so let's take that over here. So in place of the length, we'll write in our 2W plus 4. And in place of the width, we're going to plug in W plus 4. Okay, so I've modified the perimeter formula to fit my equation. And we know that altogether we have 46 feet of fencing. So we'll set 46 equal to, and now we can solve it. Does the plus 4 make sense on both of the dimensions? Because that's what the border's adding in that you have to fence around. That's usually the sticking point. Well, let's distribute and go solve. So we'll have 46 is equal to 2 times 2W, which is 4W. 2 times 4 is going to give me 8. 2 times W is 2W. And 2 times 4 gives me another 8. Now we'll collect like terms. So 4W and 2W, that's a 6W. The 8 and the 8 is going to give us 16. Okay, we'll go ahead and subtract the 16 to the other side. That's going to give me 30 is equal to 6W. And then we'll divide out the 6. That solved really nicely. So W is equal to 5. And now I'm going to reread to make sure I'm answering the question. They want to know what the dimensions of the garden are going to be. So we know that the garden itself is 5 feet wide. The length is going to be twice that. So in terms of an answer, we're going to have 5 feet by 10 feet. That's a really tiny garden. You wouldn't get much corn in there. You can't grow gourd of any kind because that's not enough room for that. So, but you end up with a 5 foot by 10 foot garden, and you're going to border 2 feet around each side of that. So again, the other geometry formulas, in case you don't remember, the area of a rectangle is length times width. And then if you're dealing with a circle, does everybody remember the formulas for the circle?
Radius is 2 pi r.
Yep. Circle. So if you're looking for the circumference, you get 2 pi r. Circumference is the distance around the outside, just like perimeters for a shape that has straight. What about the area of a circle? Remember it, pi r squared? So just in case you need those. And then for a square, back to perimeter because it's got straight sides. The perimeter would be 4 times s, where s is the side length, and its area would be s squared. I think that's about the only ones you need. For triangle, we'll need triangles later, I think. The perimeter is just the length of the 3 sides added together. So they usually write it as A plus B plus C. What about the area of a triangle? Does anybody remember that formula?
That's the base times height.
Yeah, and then what do you have to do with them? Divide it by 2. So in other words, a triangle is the same thing as a rectangle cut in half. So you divide it by 2. So nice. So just in case you need them, those are the only ones you're going to need in our class. So we did the rectangle to start with, and there's all of them together. So nice. Okay, I think your homework problem has a square on it, but we will deal with some circles later on and triangles. So there they all are. Okay, one more. And apparently this is Rich's favorite type. We're going to talk about a mixture problem from chemistry world. So example 6 says, how many liters of a 40% solution must be mixed with 10 liters of a 70% solution to get 50%? Okay, so we've got a 40% solution. We don't know how much of it. We're going to mix that with a 70% solution, and we need 10 liters of that. And we're going to get a 50% solution at the end. And again, we don't know what's going on with that. Okay, so those are the numbers that are given. I'm going to let the problem work for me. I'm going to go to that same chart where I've got an amount. I've got a percent. And then I'm going to have an amount times the percent. So this is the same thing we used on the interest problems and the same thing we used with the coffee problems. All I'm doing is changing the title to fit the problem itself. In terms of solutions, we've got solution 1, we'll call it. So number 1, number 2, and then we'll have a total. Okay. So what's really going to work for us is understanding those percentages. So I've got 40%, 70%, and 50%. So I know that 50% is between the other two, so it has to be on the bottom in terms of the total. So the other two numbers, doesn't matter in what order you put them, but there they are. They are still percentages, so don't forget that as we work this, we'll need to make them into decimals, but there they are as percentages. The only other piece of information was given is that we've got 10 liters of that 70%. So that's the amount of the 70%. Now that's different. When we worked this chart before, we had a bottom number to work with. So where the unknown is slightly different here. I do not know how much of the 40% solution, so let's call that our variable X. Okay, now what are we going to write down here is the big question. We know that we have X of the first beaker or container. We have 10 liters in the second one, and we're pouring them together. So don't we end up with X plus 10 as a total amount of liquids? So again, one beaker or container has X, the other one's got 10, and when I mix them together, we're going to end up with X plus 10 as a total. Now we're just going to multiply across. So this is going to be 0.4X. This is going to be 0.7 times the 10. And this will be 0.5. Sorry, that's a really goofy looking 5. So 0.5 times, and then in parentheses, X plus 10. Okay, then we're going to write the equation the exact same way. We're going to use this last column and write the equation writing down. So we'll have 0.4X plus 0.7 times the 10. And that's going to equal 0.5 times X plus 10. And there's our equation. So again, the first two added together equals the last one. Okay, now we'll distribute. So 0.4X plus 0.7 times 10 is just going to give me 7. 0.5X on the other side plus 5. So the numbers in this one work out fairly well. Let's move all the X's to the same side. Because the 0.5 is bigger, I'm going to actually move the X's to the right side because that'll avoid any negatives on my X's. That'll give us, and again, I ran out of room, 7 equals 0.1X plus 5. Then we can go ahead and move 5 to the other side. So we'll subtract our 5. That'll give me 2 is equal to 0.1X. And we'll divide out the 0.1. So X is equal to 2 divided by 0.1 comes out to be 20. So we need 20 liters of the weaker solution to mix with 10 liters of the 70% solution to end up with a 50% solution. So our answer is 20 liters of the 40%, which is what they're asking us as a question, is how many liters we need of that. So again, it's very similar to the other two types where we made the same similar chart. Okay, and those are the mixture problems. You have one that I think is an antifreeze problem. You're mixing antifreeze and water together. So if you do that problem in terms of percentages, water has no antifreeze in it. So when you do the antifreeze, you'll have 100%. When you do the water, you should have a 0%. So just think common sense wise. Hopefully there's no antifreeze in your drinking water. So think about it from that point of view. Okay, any question about the mixture problem? And does that make sense to everybody, I hope?
Yes.
Okay. So you have, I think it's like 8 or 9 of them to do. They're due on Wednesday. If you want to try and get them started today and then ask questions tomorrow, we definitely have time tomorrow to go over anything that you're having problems with. So any other questions or comments? It's the hardest section we see in chapter 1. Chapter 2 should be smooth sailing for the most part. Comments, questions?
I got nothing.
Got nothing?